Good morning, welcome. Hopefully you had the chance to take a quick break, and it's really lovely to have you back here. I would now like to officially open the penetration testing and intelligence-led penetration testing stream. ILPT, a bit of a mouthful. It's really, really great to see you all. Hopefully you will enjoy what we have for you today. Any first-timers in the audience? Special welcome to you guys, good in numbers as well. I'm Bogla Caronto, Bobby for short. In my capacity with CREST, I chair the penetration testing focus group, and I will have the lovely Matt Lorenzen with me later today, who chairs the ILPT focus group. So the two of us, we've put together what we think is a really nicely packed technical agenda for this stream today, and we've got a variety of topics. We're going to be starting out with LLM, which is hopefully going to fire you up before you go and get your coffee. So please welcome Donato Capitella, Principal Security Consultant at WebSecure Consulting. Donato.
Thank you. I hope you can hear me. Now, this is facing that direction, but the majority of people are here. Okay, so I know what you're thinking. Probably I forgot, or I was too lazy to make my first slide. But actually, this is the most important slide of this talk. And this could cost somebody a lot of money or could cause a lot of harm, whatever is on this slide. And I'm going to try to explain to you how this could happen in three points. So we're going to look at how Gen AI and LLM applications can be hacked. Then I'm going to share with you my mental model of why this is a difficult problem to tackle. And finally, I'm going to share some battle-tested ways that we can deploy Gen AI in production in a safer way. And I want to start from that first point. Now, as a consultant, a lot of people come to me and ask, especially a lot of clients, but if you look at the newspapers and what people are talking about, like on Twitter, these are the types of questions that people ask very often. Is this particular LLM secure? Can it be used to produce inaccurate, toxic, biased, unwanted answers? Can it be used to attack us? Now, those are important questions to ask, but I can already tell you that it's the same with the current technology. This is the same as asking whether a knife can be used to harm people. The answer is going to be yes, if that knife is good enough at cutting. So my first point here, that I think in cybersecurity at least, we should try to reframe that question a little bit differently. Let's not ask whether the knife can be used to harm somebody, but let's ask, in our use case, the way we're using the knife, and what we're using it for. Are we doing it securely? For example, if I am in a kitchen and I'm using the knife to cut vegetables, am I holding it correctly to prevent me from chopping my fingers off? That's a more interesting question to ask. That's something that we can work with. Or are we storing the knife in a way that prevents the knives from falling on somebody's feet and hurting them? I think we should do something similar with large language models and Gen AI. So when we consider the cybersecurity risk, we need to take, do I have a laser pointer? Yes, I do. We need to take whatever Gen AI language model we want to use and understand how that's wrapped up into a use case. So typically means that we are building some scaffolding application, some wrapper application, writing code that uses the LLM to do something that we want. And that use case And the code that we are using to implement the use case is providing these interactions with the external world, giving it access to documents, knowledge bases, perhaps the internet, a code base. Maybe we're making it interacting with different users, giving answers to different parties. Maybe we're giving it access to systems and APIs. Now, this red arrow, this interaction between the language model or the Gen AI and the systems that our use case requires, that's where the biggest cybersecurity risk is. So we need to threat model these and then try to find out what could go wrong. And there are a couple of things that can go wrong there. The most interesting one, and what I will talk about, are jailbreaking and prompt injection. So I'm going to do a little bit of terminology and examples, and then I'm going to give you a couple of demos. Now, I'm sure everybody's familiar with jailbreaking. You are interacting with a chatbot. The chatbot has a few rules. For example, it shouldn't give you harmful content, and you manage to convince it into telling you how to make a bomb, and you can use all different techniques. I'm sure people have seen these. The LLMs are aligned not to do this, but you can find a million different ways to bypass it. This is one of my favorite examples, using ASCII art to ask an LLM how to make a bomb and to go through all of the safeguards. Now, of course, if you are a company or one of your clients is taking something like GPT-4 and wrapping it into their customer service chatbot, obviously you can have what happened to DPD. People are going to try to make it swear, to make it say inappropriate stuff. I think in this particular case with jailbreaking, they made it say DPD is the worst delivery firm in the world. Is that jailbreaking or just telling the truth? I don't know. So this is jailbreaking. So jailbreaking requires that so the LLM takes a prompt and generates a response, and everything is text. We give it some structure. But in jailbreaking, we have a user which is actually chatting to the LLM, is actually sending a prompt, it's sending a request. It could be an instruction, and the LLM is supposed to follow that instruction. But the problem with jailbreaking is that you go out of the system instructions and the alignment, and you influence the response in a negative way. So you can have all of these kinds of unaligned responses. And my thoughts on this: do we really care if we get an LLM to tell us how to make a bomb? Perhaps we do as a society, but I don't think that from the cybersecurity point of view, this is particularly interesting. Who thinks this is interesting here? Don't raise your hand. Nobody thinks this is interesting. It becomes interesting when you have prompt injection. So the two terms are typically mixed. I think I want to separate them because they allow us to have a better dialogue. So prompt injection means that there is typically an application use case wrapped around that LLM, and you as a user, you are not providing an instruction to the LLM. It's the application that's asking the LLM to do something, taking the output and sending back to the user. And so this is a typical example. Imagine you have this application over here. The user can enter a sentence, you can click translate, and you get the translation. This could be implemented anyway in the backend. If this is an LLM application, the backend can make a prompt for the application can make a prompt for the LLM, can take the user input, which is data in this case. That's not supposed to be instruction. It's different than you chatting to ChatGPT. It can create a prompt, and then it can send it to the LLM. Now, here we can have prompt injection because this is supposed to be data, but obviously if you put instructions in there, the LLM is likely to follow those instructions. So that's prompt injection. You are just controlling some part of this to produce an unwanted response. And this becomes even more interesting, I think, for cybersecurity. If you have been distracted, tune in now, because this is more interesting. when you take that prompt injection and you make it indirect, meaning that this red bit over here doesn't come from the user that's using the application. The user that's using the application is now a victim, and it comes from a third party. It could be a document, an email, anything that comes in from there. And obviously that the output, the malicious output now targets the user of the application. I've got here an example. So this is, I am on Gmail. This is a recovery code in my mailbox, and an attacker just sent me an email. So let's say that the user is using Google Gemini Advanced. It's asking Gemini to look at the mailbox. I wish I could pause this. I realize this video is, okay, I'm just gonna try to do this again. So again, email from my bank with a recovery code, and the attacker, Mad Hatter, sends me an email. Now, I go to Google Gemini and I ask it to summarize my mailbox. Gemini accesses my mailbox, give me a summary of the 2 emails, and then look at this message which is added at the end. This message here has been injected, obviously it's a social engineering message that Gemini has produced, which has been injected by this email over here, which is telling me to go here and to get an update. And if I do that and input that thing in there, that would be the secret 5 or 4-digit code that was in another email. So again, what's happened here, that's the code. What's happened here is that the email the attacker sent in had this at the end, which is a prompt injection attack with a little bit of jailbreak stuff to instruct Gemini to go in the mailbox and find a 4-digit bank recovery code. Obviously, that could be anything, right? So that's indirect prompt injection. In this case, this is the malicious email, and the attacker is using it for social engineering. It could be used for data exfiltration and a lot of other things. If that output was rendered with Markdown, the attacker could have an image with a source, and the source of the image can be the attacker server and a parameter in the URL with whatever information the attacker wants to steal. You know, if you've done cross-site scripting and you're trying to exfiltrate information via an image, this is the same. It is not possible to do this on Google Gemini because they are stopping markdown images and links that contain information. So you just do the social engineering bit. So that's the indirect prompt injection. This becomes even worse when we start building agents. So what you've seen so far is essentially an application that sends a prompt to the LLM, gets the output, and shows you the output. What about giving the LLMs agency? In a nutshell, this means giving the LLMs tools that they can use to do actions on your behalf on the external world. So you tell the LLM, or you give the LLM the possibility to alter the external world. And I think that this is where the biggest cybersecurity risks come from when you're dealing with LLMs. Just to give an example, has anybody heard of Cognition AI? So they were on the news quite a lot a few months ago. They are a startup, and they're making a completely autonomous software engineer using an LLM. So in a nutshell, what they're doing, they're taking GPT-4 and they're giving it access to a compiler, a command line, the internet, GitHub, and file system. So you can prompt it and tell it, please build me a piece of software that does this. And they iteratively call GPT-4, and GPT-4 on its own starts creating files, compiling code, looking at the errors, browsing the internet, pulling packages in. And the promise is that this will eventually be able to write code for you. Now, that's just an extreme example of an AI agent. There are much simpler AI agents, maybe an agent that can send an email on your behalf, that's got a tool to do that. And that's definitely the future and the promise of these language models. Now, for those of you that are interested, the way, because an LLM just deals with text. or could do like sound and images if it's multimodal. We won't talk too much about the details of how you transform an LLM into an agent, but this is not a straightforward process. If you are interested, you should look up this REACT, reason and act. So the idea is that when the user asks the LLM for something, the LLM is prompted to think about what it's been asked for, and then to output a series of actions in a very specific format. You tell the LLM, you've got these tools and these actions. The LLM will output those actions. Your application parses the actions out, executes the actions, takes the output, and chucks it back into the context of the LLM. And you do this loop over and over again, and that's how you create an agent. And when you have prompt injection in an agent, this becomes very, very risky, because now the attacker can hijack the agent to do anything they want on their behalf. And I'm going to give you an example. Now, it's going to be a video of a few minutes, which I'm going to try to talk over. So what you see here is Outlook open in the browser, and then you see a plugin called Taxi AI. So Taxi AI is simply, again, an extension that you can install which transforms your browser into an agent, meaning that you give it the GPT-4 API key, and then you can prompt it to do things. So for example, open and read my emails. Now, this iteratively sends to GPT the current page. GPT can ask it to do an action. In this case, it's only just clicking on emails, but basically it can do anything it wants on the page. Now, let's see how an attacker could exploit this. So let's imagine the same case as before. I am an attacker. I want to exfiltrate confidential information from that mailbox. So I create my malicious email. Hello, we haven't spoken in a long time. And then I add these new instructions for the agent. In this case, it's telling the agent to take a banking code and to send to this email address that particular code. It could be anything, any secret we want. I'm going to make that blank just for fun. Looks like a pretty normal email. I'm going to send that in. Now the victim receives the new email. They don't want to read their emails. They ask Taxi AI to do it for them, maybe to summarize their emails. And Taxi AI starts working on the mailbox, clicking around. And then at some point, it's going to click on the email the attacker sent. And obviously, this blank part, which is actually text, is going to enter GPT-4 window, and it's now going to influence what it's going to do. And all of a sudden, the agent has been hijacked, it's got a new objective, and it's going to carry that out. It's going to go find the bank code, create a new email, and it's going to click around to essentially send that to the attacker. Boom. So that's an example of how you could use indirect prompt injection on an LLM agent to cause it to basically do whatever you want. And because we are, so again, the promise here with Gen AI is that we are going to have agents that substitute humans and are completely autonomous, like the agent I showed you or the autonomous software engineer or whatever. This is very, very risky. But wait, isn't this like SQL injection? Why isn't this an easy problem to solve? So the problem here is twofold, or you can articulate it into two different ways. LLMs really struggle to differentiate whatever high priority instruction they have been given by the application, by the system author, and whatever low priority instruction they might find. So you're talking to ChatGPT and you're asking it how to make a bomb. There is a high priority instruction which tells ChatGPT you shouldn't tell the user how to make a bomb, but at the same time, it's really hard for the LLM to distinguish that. And then obviously we have the subset of that problem with whatever the user input is, it's not a conversation. It's not even supposed to contain instructions. It's just data. So the LLM should never act on anything contained in an email that you've asked it to read and summarize. But they struggle to do this because obviously it's natural language. It's not parsing it. There's no syntax tree. There is no instructional hierarchy, no clear separation. So they are inherently vulnerable to prompt injection. So the way to think about this is my mental model for why this is really hard to solve and why it hasn't been solved. If you know how an LLM works, you kind of have an idea of the potential space of generations of an LLM, which is something around 50,000 to the power of 100,000. What do I mean by that? At every stage, an LLM functions by generating a probability distribution across for the next word or token. I'm going to use words, but you know that they are tokens, subsets of words. GPT-4 has got 50,000 tokens. So at every step, it generates a probability distribution across those. We sample one word, we chuck it back into the LLM. It generates on the entire dictionary a probability distribution. We sample from that and so on, stringing everything together. And we can go on for as long as the context size of the LLM is. Now, a few years ago, it was 2K, 4K. Today, we have 1 million tokens or 2 million tokens that models like Gemini can do. So the number of possible generations of an LLM is, again, much bigger than 50,000 to 100,000, which, if you think about it, a Rubik's Cube, 3 by 3, has got 43 quintillion combinations. That's a drop in the sea compared to this number over here, which is as big as this. It's not a very accurate way of depicting how big that number is, but it keeps going. And it keeps going and going and going. If anybody knows how to pronounce this number, this would be a good time. It's a challenge. Because of all of this space, we control but a very small part of it. That green area is what OpenAI, Google, Anthropic, it's what they're doing to give you the impression that when you're talking to their language models, you're getting good answers. They use reinforcement learning from human feedback and instruction fine-tuning. And they work by taking common prompts, common things that we would ask in a non-adversarial way, and modeling good responses for that. It's a very expensive process, and it can't really cover this entire space. This means that as long as you prompt it within this space, you get outputs within that space. It's fine. But an attacker is going to try to get the LLM to go in the rest of the space, which is much bigger and unexplored. And this is why it's really hard to secure LLMs when you deploy them in production. And what this slide is saying is that the strategy that we use today relies on trying to push the attacker and the LLM itself as much as possible towards that green area. So what does this mean? How do we do that? So, by the way, because we started, I have no idea what time we started. I have no idea how much time I've got left. I've got 5 minutes left. Okay, so I'll go very quickly. So, to deploy LLM applications in production in a secure way, or as secure as possible, we have to do a lot of things to push the attacker into that green space. First of all, treat the LLM as untrusted. The input to the LLM needs to be validated. Now, this validation can't just be your classic format validation. You need to do some semantic validation using models and classifiers to try and detect whether in the input you've got something that's unexpected. This is a hard problem, and it will never be perfect. So if you're trying to use a model like a sentence classifier to check whether the input semantically contains a prompt injection attack, it's a probabilistic approach. You are reducing the space of operation of the attacker to that green area, but there is no guarantee that the attacker doesn't find something that they can still use. But anyway, this reduces the space of operation. And obviously, you do spotlighting. Those of you that have done some prompt engineering, I'll just put it there. You can try to structure your prompts in a way where the user data or user input is more salient to the model, and it's more difficult for an attacker to do a prompt injection or jailbreak. So the inputs need to be tested semantically, and the data and instructions need to be separated as much as possible. And then you do the same on the outputs. You check the same things that you would check in the input. You check if the model has generated something you don't want. Now, you can do this with other models, with other classifiers, but also you want to filter the output in a deterministic way. For example, you should not allow markdown images. You should not allow the LLM to give HTML links or stuff like that. LLMs love on their own to hallucinate links. If an attacker is prompting it adversarially, that link can be very dangerous. So typically, and what Google Gemini, for example, does, as soon as their LLM gives out a link, they look at that link, and if it's more than a basic domain name, if it's got any subdomain, if it's got anything in the URL that they don't like, they will immediately kill your entire session. You can try. So they're being very aggressive with this. And typically, you don't want markdown images and stuff like that. And obviously, content security policy can help. The kind of things that we typically do for normal applications. And if your LLM has got access to tools, so if it's an agent that can interact with the world, our usual access control should apply. I mean, never trust. I mean, if you tell the LLM that it shouldn't do something, do not trust that the LLM is not going to try to use that API to do it. You should obviously do a downstream check. Similarly, we got a challenge last year at B-Sides where we exposed a vulnerable API to an LLM. It was an API vulnerable to SQL injection. And as part of prompting it, you could teach the LLM how to exploit the prompt injection in the API it had access to, the SQL injection in the API it had access to. And finally, human in the loop. So something that performs actions on behalf of a human should have some approval mechanism. So the LLM should give you the plan, you should approve the actions, it should never be left to do it autonomously. And I think this is all the time we have. I'll just mention a few things and then I'll stop. The other way that you can do it is to try and expand this green area. This is for people that build models. They can try to make models that are more resilient. There is research in the area. I'm just going to mention research at Microsoft to try and solve this part of the problem, differentiating data from instruction, and research at OpenAI trying to do the other part, differentiating high priority instruction from lower priority instruction. The nutshell takeaway from this, it doesn't work. And that's all I have for you. What's on this slide could cost you, your businesses, a lot of money. Thank you very much for your attention.